was you have a kid run towards the merry-go-round. They're going to jump onto the merry-go-round, and then the kid and the merry-go-round are going to go in a circle. So this is a conservation of angular momentum question. It is a collision. And if you want to understand the way my mind sees this question, I have a whole litany of follow-up questions that should follow it. Things that are more like what you've seen in your homework, like you should prove how linear momentum is not conserved in this instance, because it isn't. Linear momentum isn't conserved because once the kid jumps on the merry-go-round, they stay in place. There's a fixed point there. You can actually find the force on the system from the kid jumping on there by looking at what happens to the pivot point. So there are clear indications that momentum is not conserved, but angular momentum is conserved. So we have two conditions in this problem. We have this condition here where the kid is just running and the merry-go-round is not moving. And then we have this condition where the kid is now on the merry-go-round and the system is spinning. So like any good collision question, I think you should kind of break it up and have a before side and an after side and set them equal to each other. Now, the left side is going to be the angular momentum of a point object running, in a straight line. So we're talking about R cross P. And I was talking with a couple students yesterday, and this became an issue. I realized, and I went back through some of my notes today, I'm not consistent. Sometimes I will put an X when I mean multiply. I saw that I did it a couple times when I was indicating, well, there's two of these, so you multiply by 2. And I'll put an X there, and then sometimes I put an X when I mean cross product. So let me be very clear. The X here is the vector cross product. It is the way you multiply two vectors together, and you should have something about this in your notes, cross products and dot products. Because I say those words, cross products and dot products. There's two different ways to multiply vectors. And when I say different ways, it's not like you choose on you call an audible when you're about to multiply and pick one. They serve two different functions. A cross product is trying to figure out how much of the first object is perpendicular to the second, how much of the first vector is perpendicular to the second vector. Meaning a cross product is maxed when they're at right angles to each other. It's the open the door thing. If you want to open a door, you push perpendicular to the door to get out. That's how you get maximum torque. It's a cross product. Dot products are different. Dot products are a maximum when the first vector is in line with the second vector. So work is a dot product. You get maximum work when you push the object in the direction you want it to go. So the force is in the same direction as the displacement, you get max work done. If you push up on a chair that you want to go forward, that's not working out for us, is it? So again, dot products are maximum at when the angles are in alignment, so it uses cosine. Cross products are maximum when the vectors are perpendicular, thus the sine. So this is a cross product. And the two vectors are, in this case, R, which if I was to draw it right now would be that, and the momentum, which is this one, and we'd be focused on this angle between them right there. But let's be honest, I didn't tell you where the kid started running. So it's not like you can actually use that. Your notes, a big box should be there to talk about where is it that contact is made. Because that's the R you're going to use. And in almost every circumstance, not 100% of the time, but in almost every circumstance, you're going to look at where the objects connect. And that's almost always going to be a perpendicular distance. Not every time. I'm going to show you an example where that's not true. But in this circumstance, I'm trying to start easy. Just accelerate your guy to a place you know, and we know he's going to actually hit right here. Tangent to the edge of the merry-go-round. The word tangent, we know we're talking about a line that touches a circle at only one point. That's a tangent. We're good for that? I hope so. Maybe not. If you don't know that word, you should learn it. So I'm going to take my R perpendicular. I'm going to replace this with MV and recognize at this point that it's sine 90 degrees because we are hitting that right perpendicular. A tangent is perpendicular to a radius of a circle. That's the left side. Let's handle some things about the right side. The right side is after the kid gets on there and the system is going to rotate. This becomes a I times omega. Remember the difference between lowercase l and uppercase L. Oh yeah, be nice to the E&M kids. They're learning a new topic today whose symbol is also uppercase L. And neither one of them actually start with L. So angular momentum, uppercase L, and inductance, uppercase L. And neither one of them start with L. Which is funny because it also has current in it, which is an I, but inductance starts with an I. Gonna love E&M. So, I see that there are two objects here. So I'm going to break this up into the moment of inertia of the merry-go-round plus the moment of inertia of the kid. Do you see that? And then omega. So our job now is to just kind of, we have almost all the values to put this together. But in case we haven't done all of our due diligence, the merry-go-round is 1/2 mr squared. The kid is a point mass that has jumped on the edge, so he is just mr squared. That's omega. Now, left side, R perpendicular is just the radius of this particular ride. M is the mass of the kid, and V is how fast he's going. Now, truthfully, one of the R's cancels out here. If you really want to do the work, and solve it, algebraically first, and then put your numbers in, then you could cancel out one of the R's. But I don't know that it matters. We knew it was a 1.5 meter radius merry-go-round, and he was running at 3 meters per second, had a mass of 60. So that's 1.5 times 60 times 3 meters per second. That's the left side. My 3 looked like a 6. Okay, I'm going to have to believe you.
I think it's because you zoomed out really far. I don't know. I think that explains why I got a different answer.
I really enjoy Allison's company. Now, I've said my 3 looked like a... I don't look like anything. 3 looks like a 3. I don't have terrible handwriting. 1/2 times 150 times 1.5 squared plus 60 times 1.5 squared again, omega. And there it is. That's it. That's all I had to do. I think this is like 0.89 radians per second. Somebody do me a favor. Tell me what 0.89 times 1.5 is. It's a little less than 1.5, obviously, but... 1.335? Yes. So the kid was going at 3 meters per second just before they land on the merry-go-round, and after they land on the merry-go-round, their linear speed, 1.335. I'm pointing this out not because I think it's super important, but because it shows you that because I mean, we get an angular speed, but a lot of you have no idea what 0.89 radians per second actually is. I don't know that I have a good feel for what that is, but I know that the linear speed is something I have a better feel for. The kid clearly slowed down, and the kid had to slow down so the merry-go-round could speed up. And I think that makes perfect sense. I bet if we calculate the kinetic energy of the kid before he jumps and the kinetic energy of the system after, we're going to find that it's less. This is an inelastic collision. And if you want to know the kind of questions I'm going to ask on a test or the things that would be on an AP exam, that would be one of them. I think it would be perfectly suited to you guys to figure out what the initial kinetic energy was, 1/2 60 times 3 squared. I'm just throwing it out there because your first homework question does this stuff. And then what is the final kinetic energy afterwards? 1/2 times all that garbage for the moment of inertia, which I'm not going to do again, times 0.89 squared. I am very confident that there's energy lost in this collision, just like in any collision. But any questions about this so far? So I'm going to cover something that I was unable to cover in this class due to our time, but I want to make sure we've got this problem down. All right, so I can move on? Okay, moving on. We can do the same thing with the right-hand rule to prove that after the collision, the merry-go-round is going to spin out of the board towards you. Make that nice and big. R. All right, that velocity is, I'm totally blocking the projector. R, I have to line my hand, this one up this way. My thumb is clearly out of the board. You guys look great doing it. Keep it up. Clearly shows my thumb pointing out of the board, so the angular momentum of the kid as they run this way is out of the board. And when they jump on there, I'm expecting the system to rotate that away, right? Same idea here. And although you may never have to use the right-hand rule in this way, this convention is here for two reasons. One, to give us something to latch onto, to understand how these things are related. But also, the mathematics of this has to be consistent. A machine can't do the right-hand rule. So the idea of positive and negative in multiple dimensions, that can be done by a machine. So this convention is there to ensure that a machine could calculate this, or that I could convey it to somebody who's not in the same room. I can't tell somebody who's not in the same room, point in the direction of the green arrow. I can give them coordinates, though. I can say if these are the coordinates of the green arrow, they could calculate the direction of rotation then. Now, in order to simulate gravity on a space station, to create this normal force, we would like that normal force, which would be the unbalanced force acting on them, to be as big as the weight of the person. So that would mean a centripetal acceleration that's equal to g, 10 meters per second squared. Now, it only takes a few hops, skips, and jumps to get to the answer here, which is, if you want to know how fast to spin it, once you know the radius, you can just plug that in and figure out what the speed has to be. Now, in reality, this is not as simple as it sounds. People can be fooled. Of course, they would notice that the floor is curved, and it would probably be okay, but the ear is still being spun around, so people get dizzy. So you can simulate gravity, but you actually have limits on how you can do this effectively and not have people get sick all over the space station. So you have to make the radius big enough where it spins slow enough. You clearly see that there's an inverse relationship here, right? If r gets bigger, omega gets smaller, so you can spin your spaceship slower. and the people have less chance of throwing up on your space station. So a lot of movies have talked about this. What the movies fail to discuss is that there's people walking around on the inside of the space station. So let's say, for poops and giggles, that the space station already has some omega. And there's people in the space station. They are stationary with respect to the space station. Good so far? What happens when this guy decides to run that way? Go ahead.
What is perceived gravity?
I think several things will happen. I think that's one of them. If he runs that way, his linear speed will increase. We get to take the angular speed of the spacecraft, add his linear speed, and suddenly he's going to feel heavier as he runs. Suggesting to me that if you're going to use this for exercise, which they always show on these stupid things, people running around in a circle, then he may wish to run this way. Right? He'll feel lighter if he runs this way. Of course, if he runs fast enough, he floats again. You understand that too, right? If he can run fast enough so that he's actually not moving relative to space, his velocity could be 0, and now he's back to floating. You understand what I'm saying? Now that's one problem here. That running in the space station is an issue. These movies never handle it. They always just say it's no problem, they can run around in a circle. I think problem. But let's say that that's not the biggest problem. The other problem is this: if there's nothing acting on the space station, and he begins to run in the same direction it was already spinning, doesn't his angular momentum about the center go up? Because he's now traveling faster in a circle than the space station is. Wouldn't conservation of angular momentum suggest that the space station has to slow down? Him running inside the space station is going to affect the speed of the space station. And this one is super easy to understand. If he pushes himself forwards, Newton's third law says he pushes the space station backwards. So for him to be pushed this way, his force on the space station is going to be that way. That will slow the space station down. You follow along? The real question is, if he's running, say, 1 meter per second relative to the space station, the problem is that that's relative to the space station, and the space station's moving. This problem can become quite complex really fast, as you can probably see already from my just short conversation. So we will look at the railroad version of this problem tomorrow. It's a little simpler than the space station version. I like the space station version because it includes this little thing about artificial gravity in it. It makes for an interesting question. I ask this question on your homework, and I've given you a kind of a good start on it. And the homework question, I make it so that a whole bunch of people all go for a run at once, so they have a mass that is actually big enough relative to the space station to make a difference. And that's what makes that problem interesting. And we'll talk a little bit about how to deal with that problem tomorrow. Well, there's 1 minute left, and you guys have been... So, yesterday, we were talking about angular momentum for a point particle or a particle traveling in a straight line. We handled how it's calculated, and we were able to, I think, successfully prove that R cross P is constant for an object whose linear momentum is not changing. That's what we spent all that time doing yesterday, showing that even as the object got closer, that although R got smaller, the angle got bigger in the same proportion. You guys remember that conversation yesterday? So I want you to imagine kind of 4 states of this problem. And in each one of them, there's a different R that needs to be drawn to be used in calculating the angular momentum. So what I mean by that is, in each case, there is a vector that points from this particular place to the center of each object. Well, maybe not each object. Each object is the wrong word to use there. There's one object, and it just has a velocity as it's going sideways there. R cross P has to have direction because angular momentum is a vector quantity. And the right-hand rule should be able to be used to tell us the direction of the angular momentum. But remember, we are talking about the spin. Angular momentum refers to something that is spinning. And clearly this object isn't spinning, it's traveling in a straight line. And our point of observation right here, this is our point of observation, is where all of the R's are based. The R's all start here. Technically, I should be able to use my 3-finger rule to determine the angular momentum about this point. Let's give it a name so I can refer to it. We'll call this point P. That we're talking about the fact that my disk has an angular momentum about point P. Now we're choosing our point here. I'm just giving it a name so that I can refer to it and point at it. So, right-hand rule, if you'll remember, for torque, it was first vector, second vector, result. So when we talked about opening the door, remember, if I push here, then the first vector, R, is the arrow drawn from the hinge to my hand. The second vector is the force, which is outwards. So the torque would be downwards through the hinge. And indeed, the door will open outwards like we expect at 325, I'm sure. So I should be able to use my right-hand rule here for R cross P. R goes that way. To line this finger up with the velocity, I need to kind of flip it over. Because even though it's a pretty wide angle, it would not work for me to try and do it pointing this way. I can't get my finger up on the other side of my hand. So I need to flip it over. And I can line them up if I flip them over, telling me that the angular momentum of this object about this point is into the board. Now, that doesn't seem to make a lot of sense because we don't really see anything rotating. And that might make this hard, but I drew R as a green line. Do you guys see the green lines on the board? If you imagine this thing passing by point P, the green line would sweep around point P in this direction, which is why we say the angular momentum is indeed into the board at point P because of how R sweeps around point P. So the 3-finger rule and our right-hand rule engagement is connected in both of these sets. Even though nothing appears to be rotating, we still have a convention that connects the direction of this angular momentum together. And explains, of course, in our collision, why the merry-go-round spins in the direction it does. So if we go back to this one, over